right, so for torque, here's our notes. So an axis or a fulcrum, it's any point of rotation. Examples are like your door hinges, Earth's axis, the head of a wrench. So dealing with this pivot, this turning, right? This is what torque's going to be. It's going to be the tendency of a force to cause an object to rotate about an axis. All right. And one thing you also need to make note here is that the force must be applied perpendicularly to the object. We'll kind of explain that with some examples here later. Okay, torque is just a force, so it's going to be newtons, capital N. Okay, and our formula for torque is like a weird kind of cursive-y T looking thing. It'll look a little different like on our formula sheet and stuff, but it's very similar, just like a little capital T. Okay, is equal to force times the radius. Okay, force times radius. So sample one, if a force applied perpendicular to the end of a bar of length that's 0.5 meters. So there's the bar that's 0.5 meters. From the fulcrum creates a torque of 10 Newton meters. Okay, oh yeah, sorry. Newton, the units are Newton meters. Newton meters. Yeah, I forgot because it's the force times the radius. Okay, 10 Newton meters. What is the magnitude of the force applied? Okay, so we're given torque, 10 Newton meters. We're given the length, which is going to be our radius, of 0.5 meters, and we're solving for force. All right, so formula, 10 equals F, what I'm solving for, times 0.5, divide by 0.5, divide by 0.5, get a force of 20 newtons. Okay. Which way will it twist? This is where we know it's positive or negative. Okay, because we know force is force in like radius and distances and stuff. We like to have, positive, negative directions on it. So torque will cause an object to twist clockwise. If it's clockwise, in other words, it goes with the direction of a clock. Okay, so clockwise is going to be a negative torque. And if it's going counterclockwise, that's going to be a positive, kind of backwards of what we want to think. Clockwise is positive, right? But no, it's actually opposite. Keep that in mind. All right, determining if the force applied will cause torque. 4 things we look at. We identify the force in each of the following situations. Decide if the force is perpendicular or parallel to the object. Determine if it causes torque. And determine if the torque is positive or negative. Okay, so pushing a child on the back while he or she is on a swing. Okay, so I'm just going to draw like a little picture. Here's the bar. Here's the chains of the swing. And here's the seat of the swing. All right, and here's the kid sitting on the swing. Woot, woot. And here you are pushing on the back. So we're going to be pushing to the right. I know it doesn't say it, but I'm just going to determine right now we're pushing to the right. Okay, so the force of number 1, identify the force. Okay, the force is going to be the force applied. Okay, the force applied is the push on the back. That's obviously coming from you. Let's see, is acting perpendicular. So if this is my object, this is the back of the kid, it's going this way, right? and my push is going this way. So yes, perpendicular. All right, number 3, determine if it causes torque. Well, we're going to see this kid rotate about this axis right here. So yes. And determine if the torque is positive or negative. In this case, if I'm going this direction, I'm going against the clock, so I'm going counterclockwise, which is positive. All right. So B, child's weight acting downward on the right side of a seesaw. Again, so here's my fulcrum on the right side of the seesaw, sitting here, and weight is going this. All right, so the force is the force of gravity, also known as the weight of the child. Okay, that force is acting down. The seesaw is this way horizontally. So yes, perpendicular. Is it going to cause a torque or a rotation? Yes, it's going to rotate about this axis right here. So yes, there is torque. And in this case, we're going with the clock. So clockwise is negative. Okay, wiping dust off the face of your TV screen with the palm of your hand. All right, so here's my TV screen. Okay, so notice that the TV screen is sitting this way, and if I'm wiping dust palm of my hand, the force applied is from my hand. Okay, is it perpendicular? So if my TV screen's going this way, and I'm also wiping this way, okay, then no. It's not perpendicular. So no, there will be no torque because I'm just wiping it off the TV. I'm not spinning the TV. I'm not turning the TV. So there would be no, it's not positive or negative because there's no torque and no rotation. All right, going on to the back page. So I know it says review. We haven't really talked about it yet, but centripetal acceleration. Okay, so just FYI, if we ever see the word centripetal, okay, the century looks like the word center, and pedal just means seeking. All right, so we were talking about objects that move in circles. Objects, let's just say objects moving in circles, accelerate even if the speed of rotation is constant due to direction change. Same thing we've always said about acceleration. It's speed up, slow down, or change directions. If I'm moving in circles, I'm constantly changing directions, so I have to have an acceleration there. Okay, Newton's second law states if an object is accelerating, then the forces are unbalanced. So there has to be some kind of force causing it to continue in a circle. Let's see, second law in torque, rotating. So a rotating object accelerating. Oh, a rotating object is accelerating. Is accelerating, and therefore the forces are unbalanced. So my acceleration would not be equal to 0 because we're changing directions. Okay, so formula. So if I talked about the sum of torques, remember my net torque, sum of torques, net torque, okay, would not be equal to 0. Kind of like my net force would not be balanced, my net torque would not be balanced. In rotating objects. Static equilibrium, which is like a stationary object, something that's not rotating, right? Stationary object has balanced torque applied. So if we balanced out that seesaw on both sides, it wouldn't rotate. And the net torque in that case would be 0. All right, so for example, 2 children are playing on a seesaw. The 35-kilogram girl sits 200 centimeters away from the axis, and the boy sits 150 centimeters away from the axis. If the seesaw is not rotating, what is the mass of the boy? Hint, if it is not rotating, what do you know about the sum of torque or the net torque? If it's not rotating, we know it's going to be 0. Think about which way the objects are causing it to rotate, positive or negative. All right? So if I'm talking about a seesaw, right, and I want the torque of the girl has to equal the torque of the boy in order to be 0, in order to balance out, right? They need to balance each other. Okay, so to solve for the torque of the girl, I could do the force of the girl times the radius. Same for the boy, I can do the force of the boy times the radius. Okay, what's applying the force here? Well, if it's on a seesaw, it's just going to be the force of gravity, right? So this force would just be the weight of the girl times that radius. Same with the boy, the weight of the boy times how far is he from the fulcrum. So how do I solve for force of gravity? I do mass times gravity, right? So mass times gravity times radius equals mass times gravity times radius. This Fg is equal to mg, and then just carry down the r, carry down the r there. So let's see what we got here. Let's put in our mass. So the mass of the girl was 35, gravity negative 9.8, and she sits 200 centimeters away, which is 2 meters. The mass of the boy is what we're solving for. Gravity negative 9.8, and he sits 150, which is 1.5 centimeters away. I need a calculator. Let's see. Calculator, 35 times 9.8 times 2, 686. Mass, and this is 9.8 times 1.5, 14.7. Right? If I divide both sides by this 14.7, I get 686 divided by 14.7. The mass of the boy is 46.67 kilograms. And mass, even if I did get a negative, you knew that mass couldn't be negative. Okay, so if something's balanced, the torques have to equal the same. All right, and that's it. Y'all go ahead and get that practice done. Thank you.